Okay, so we were talking about CSPs in the last class. This is what we have to remember, as it's a special subset of search problem, so we are still continuing our topic of search. State is defined by variables xi with values from a domain D, and D sometimes depends on I. So basically variables xi and domain D. Goal test is a set of constraints that specifying allowable combinations of values for subset of variables. Right? So we had seen this example. The problem given is you are given a map of Australia and you are also given. So what are variables in this case? What are variables in this case? RGB is your domain. So what are variables in this case? These states, right? Western Australia, that's how we are assigning them, or at least that's how they are assigning them. So we talked about these things. Variables are 7, all these states. Domains are red, green and blue. This will be assigned to whom? Each of the variables, right? So each of the variables can take these 3 values. Now whether that coloring is legal or illegal, who decides that? Your constraints. Okay? And we continue. So let's talk about this in Queens now. Okay. All right. What is happening in this? So what is n queens? Heard of this problem before? What is it? Right. So you are given a square chess grid of size n cross n. How many queens you have to place in there? N. If you place n plus 1, can you solve this problem? Right? Because then you will have at least one pair which will be attacking each other. So a grid is n cross n and you are given exactly n queens. You have to place them such that no pair of queens attack each other. Okay? Is this a solution? Right? In this case, nobody is attacking anyone. So how can we formulate it? Remember, we have to come up with these 2 things. What 2 things? We have to come up with 2 things. कौन सी 2 चीजें थी? Variables and domains. Variables क्या रखोगे इस केस में? So let me help you there. Right. Variables are xij. We are formulating in that manner. Xij means, so how many total variables will be there? N square in this case. So let's forget n now. Let's talk about this 4 cross 4 grid. So how many total variables in this case? 16. And what does this mean? So either you have a queen or you don't have a queen there. What can constraints look like? Not a? Right. So how do we express this in terms of these? So same row, same column and same diagonal. We don't want another queen. Okay. So what is this guy? Tell me what is this? What is Xij? A square, one of these. So it's a position. It's this small square. What is Xik? Again a position, right? So one position comma second position, it's a tuple of positions, should belong to this. What does it mean? And have you noticed something here in this case? I is same, right? What does this mean? If I put I equal to 1, so I am talking about first row. So x1j, x1k for all j and k. So I am talking about this one. What should happen? Either. So in this figure, what is x11 comma x13? What is x11 comma x13? 0 and 0, right? What is x11 comma x12? What is x11 comma x12? 0 1. x11 is 0 but x12 is 1. What about x12 comma x14? x12 comma x14? 1 0. So we understand this. What is this constraint giving me? What does this constraint imply? So which possibility is left out? 1 comma 1, right? So if this happens, that means you have exactly one queen in the first row, so nobody will be attacking because of this row. Now you said for all I. What does this mean? For all rows, when I equal to 1, when I equal to 2, I equal to 3 and I equal to 4. Can you give me the next constraint? Next logical constraint would be for columns. So can you give me the next one? Will this part remain the same? Right? So then where will for all ijk remain the same? Yes. So we'll have a change here. What will that change be? Sorry, say that again. xji xki, right? So something of that sort. xij x kj, we have this second done as well. Third one. So if you talk about this position, you have talked about this, you have talked about this. Two things are still left. This diagonal and this diagonal. So I'll show it to you. Now, is this fine? Dekho, this is going to remain same for all, right? We don't want 1 comma 1, rest everything is fine. Now these two are there for you. What is this? So if I am at x11, okay, what happens here? So I is 1, j is 1, and I add, let's say k equal to 2. So I go from 1 comma 1 to 3 comma 3. So I travel along this diagonal. But let's say, so 1 1 was maybe an easy case. Let's say we are at 1 comma 2. So not 1 comma 2, let us stick to, no, let us stick to what we have been doing. This is x1 2. So x1 2, I is 1, j is 2. How do I translate now? If I add 2 now, x 3 4, is that right? X 3 4 takes me here. So this is helping me walk along which direction, which diagonal? This one. Okay. What about this last one? This one? Figure out. Okay. So we have talked about all the manner in which a queen can attack. So if you ensure that for this given place, there is no queen in this column, there is no queen in this one, there is no queen here, there is no queen here. For this queen, you have ensured that there is no one attacking to this queen. And if you ensure the same constraint for all of them, then basically that's a solution to our problem. Any questions in this regard? Okay. Are we done? कुछ बचा है? We often forget this. Trivial, you guys know it, but we still forget this. What is it? Mathematical constraints के हिसाब से we have written everything, but one thing, one trivial thing is remaining. What is it? Okay. What will be summation xij for all ij? What will be summation xij for all ij? It has to be n, right? So this is an important thing. Trivial, we know it, but we forget to incorporate this. So this is the formulation of our CSP for n queens. ये प्रॉब्लम के बारे में पहले सुना है, जानते हो? इन प्रीवियस कोर्स किसी कोर्स में किया हो? नो? ओके. अच्छा, इन सो डू यू नो अबाउट NP completeness? What is it? This course is on AI and we'll be talking about problems that are NP complete. Let's go next. So that was one formulation of the problem. Okay? कोई बात नहीं. We'll do NP completeness. Come back here. N queens, another formulation, right? So this time I'll give you the complete formulation. Variables qk, domain is 1 2 3 4 n, constraints are this. Okay, what is happening in this case? मेरे को बताना. This one you figure out. Okay, we have talked about one formulation extensively, you figure out this one. But it is analogous to that one. That was for one square, this one is for one row. Okay? Alright, go next. Constraint graphs. What is this? You have seen it before. What is this? This is the graph for the coloring problem of Australia, right? So what was this name? Western Australia. This was Northern Territory. This was South Australia. This was Queensland, New South Wales, Victoria, Tasmania. Okay. So this is how they are connected. How should I color them? We need to formalize this problem as well now. Okay. So constraint graphs, binary CSP, each constraint relates to at most two variables. ये चीज समझ लो. I won't ask what is a binary CSP, but you need to know what is a binary CSP. I might use just this term in the questions in exam. So each constraint relates at most to two variables. What does this mean? So each constraint relates to at most two variables. What does this mean? So I have two adjacent nodes here. Is that what you are saying? Because for this guy I have 5 neighbors. What does this mean? It does not matter how many neighbors this guy has. You will still compute. So if there are 5 neighbors, there will be how many constraints? 5. 1 for each. Right? So each constraint relates at most two variables. There lies a constraint here. Right? There is no constraint like this, where you have to take care of all these 3 at once. Okay? There is no constraint that involves 3 variables. You have pairwise constraints. This guy cannot be same as this guy cannot be same as this guy cannot be same as this, but there is no constraint over 3 of them at once. Okay? Binary constraint graph, nodes are variables, arcs show constraints. So these are my variables and arcs show the constraints. General purpose CSP algorithms use the graph structure to speed up search. So I mean, this is all of you can do. This is a independent component of this graph. So whatever we are doing here, that does not affect this one. So that is trivial. Okay, all these examples, I just skip them. What happens in case of Sudoku? Can you formulate constraints for Sudoku? What in plain English words, what will that be? Row should sum to same number and one more constraint? No, digits can't repeat. Right? So row, column and this block, right? So they have to sum to the, I mean they will of course sum to the same thing if you have all the different digits from 1 to 9. Okay? Variables, each open square. Domains are these. Constraints. Okay, and so on. So this is how people used to do computer vision earlier, but we skip this. It's not done this way anymore. Okay. Discrete variables. We'll be talking about discrete variables. What does it mean, discrete variables? So in case of graph coloring problem, we had 7 variables. In case of n queens, we had how many variables? N square, right? 16, and so on. Finite domains. What does it mean, finite domains? Domain was red, blue, green, finite. In case of n queens, domain was 0, 1, finite. In case of Sudoku, domain was 1 to 9, finite. Okay? Finite domain size D means order D to the n complete assignments. I want this answer from you. What is order D to the n complete assignments? No, my question is here. What is order D to the n? What does it mean? Size D means order D to the n complete assignments. Easy, you can do it. What do you mean by complete assignments? All variables are assigned some value, right? So how many total such assignments can be there? Yeah, D is domain size, n is variable. So how do I get D to the n? My question is, how do I reach there? Why D to the n? Why not n to the d?
For each variable we have to put every domain.
Right. Right. So there are n variables. How many possibilities for this guy? D. How many for this? D. D to the n. Okay. Now, so these many complete assignments are there. We are not talking about whether they are legal or not. We are saying just total complete assignments. Example, Boolean CSPs including Boolean satisfiability is NP. Heard of SAT before? SAT? What is the full form of that problem? So what is satisfiability? Boolean satisfiability? Heard of this before? Okay. And what did you do with that problem? Try to find a. Okay, right? And अच्छा एक बात बताओ, order D to the n. So D in my coloring case was 3 RGB. N, if the graph is large enough, can be huge. Okay, let's say n is 100. Is this number even feasible? It is 3 to the 100, right? You can't enumerate all the. So what we are saying is, you can't really enumerate everything and then decide which is a feasible solution. That does not work. Okay, all those problems from which, very roughly, very vaguely speaking, brute force is not the right way to do it. Most likely that's a NP complete problem, right? But I won't go into the details of NP completeness right now. Infinite domains, integers, strings, etc. Job scheduling variables are start and times for each job. Linear constraints, non-linear, undecidable. So heard of undecidable problems? Theory of computation is done? No. Okay. Continuous variables, I don't think we talk about these at all. Okay. So that's what they say. Varieties of constraints. Unary constraints involve a single variable equivalent to reducing domains. For example, South Australia cannot be green. Binary constraints, south of Australia cannot be same as Western Australia. Higher order constraints involve 3 or more variables. Okay. Preferences, So you can have preferences. You prefer red over green. Often presentable by a cost for each variable assignment. So basically you can have, apart from these hard constraints, you can have some soft constraints that I want it in this manner. Okay. CSPs are everywhere. Scheduling problem, timetabling problems, assignment, hardware configuration and so on. Now we talk about solving CSPs. So there is a standard search formulation of CSPs. States defined by the values assigned so far, initial state, successor function, goal state, and we'll start with the straightforward naive approach, then improve it. So how do you think we are going to solve these problems? Same search, okay? They are subset of search problems. So if, let's say, this is your set of search problems, CSPs are here. They are specialized, special ones. Standard search formulation of CSPs, we need, and the moment you say we are talking about search formulations, there will be an initial state, there will be a successor function, there will be a goal test. What would BFS do? What would BFS do in this case? Tree banao. I mean, imagine karo tree if you don't want to draw it. Start state will be, what will be my start state? Very good. Start state is ऐसे, और कहाँ जाना है मेरे को? So goal state is Tasmania? कुछ भी. So T तक जाना है. T तक जाना आपको? But was anything special with South Australia? So if other friend of yours decided to start from T, anything wrong with that? Huh? So we are not stating the right start state. Start state is something you look at it and you figure out this is my start state. What is start state? ऐसे फिर से. And what is so special with WA? So what happens if I just flip this? Problem does not change. Question is, what is my start state? What is my problem at hand? You have to assign a full color assignment, right? So this is my start state when nobody is colored. Okay? What will be the next level of states? One colored. So how many total such states will be there? 7. How many colors do I have? What is my domain size?
3.
So 7 into 3? 21. I can have 21 states in the next level. How many states in the last level? Seven? 21 into 7 into, so 21 square. Okay, how do you get that 21 square? ये सारी चीजें अपन कर चुके हैं पहले ही. Last level is the level of complete assignment. Total number of states will be 3 to the power. Remember d to the n it was? So 3 to the power 7. And it includes all color assignments. For example, all blues, all red, all green, one green, rest all blue, and so on. Every possible configuration is there, right? So you understand this whole tree now. What is at the root of this tree? What is at the root of this tree? This graph without colored. What is at the last level? All assignments, complete assignment level. Okay. Now, who decides which assignment is legal or not? Constraints, right? So here my constraints tell me that all blue is not legal, and so on. Okay. Now tell me, so you understand this tree, right? What will BFS do? What will BFS do in this case? अटेंडेंस यार ईआरपी पे आ गई क्या अटेंडेंस? बाकी लोग ले रहे हैं?
यस सर, ले रहे हैं.
ओके, फ्रॉम टुमारो आई विल स्टार्ट दैट टू. हाँ, व्हाट विल डीएफएस बीएफएस डू, ये है क्वेश्चन. What will be the time complexity for BFS for this CSP, this particular CSP? किस चीज में टाइम लगा रहे हो भाई? What will BFS do? हाँ, कॉपी की जरूरत नहीं है, पर ठीक है बना लो, कर लो, बनाओ, सारे लेवल बनाओ, मेरे को सब पूरा लास्ट लेवल तक दिखना चाहिए. हाँ, यू आर सेइंग समथिंग, कुछ तो बोल रहे थे. हाँ, 3 to the power 7, right? So what is that? Time complexity. Because I cannot have a goal anywhere before the state of complete assignments. भाई जब तक आप 6th लेवल पे हो, एटलीस्ट वन वेरिएबल इज येट टू बी असाइंड अ वैल्यू, सो यू कांट चेक फॉर कंस्ट्रेंट्स. योर ऑल द गोल्स लाई ओनली ऑन द लास्ट लेयर. सो व्हाट अबाउट बीएफएस इन दैट केस? d to the n. Okay, wait, there are no. What will DFS do? So in the worst case both are d to the n. Okay, now which one would you prefer, DFS or BFS? BFS. क्यों? There is no shallowness here. DFS, because I might hit a goal before. BFS, so I know it will first explore everything and then reach to the last level. Okay. What problems does this naive search have? We have already discussed that. That's what we have been discussing. backtracking search. So if you will involve backtracking, कौन से एल्गोरिथम के साथ लगाओगे? BFS or DFS?
DFS.
For BFS it does not make sense, okay, but DFS में, let's say so how long will you take to one complete assignment if you are using DFS? I repeat my question, कितनी देर में स्टार्ट रूट से एक कंप्लीट असाइनमेंट के रूट तक में नोड तक मैं पहुंच जाऊंगा? 7. All right, so it is the height of my tree. It is linear in the height of my tree. Now that might or might not be satisfying my constraints. Okay, in that case what do I have to do? I have to do backtrack and keep on doing that. Okay, so backtracking search is the basic uninformed algorithm for solving CSPs. One variable at a time. Variable assignments are commutative, so fixed ordering. What is commutativity? Nahi. My question is, what is commutativity? A plus B equal to B plus A, right? If WA equal to red, then NT equal to green. This is same as NT equal to green, then WA is red. Only need to consider assignments to a single variable at each step. Idea 2, check constraints as you go. That is, consider only values which do not conflict with previous assignments. Might have to do some computation to check the constraints, incremental goal test. This is what we have been doing. कि भाई सब कुछ कलर कर दिया, अब देखते जाओ कि which of those final states that is not violating the constraints. Depth first search with these two improvements is called backtracking search. Not the best name. Okay. What are these two ideas? One variable at a time, right? So you assign color only to one variable at a time and check constraints as you go. एक बात बताओ, do you necessarily have to reach to last level to figure out कि constraints are violated, right? So can you give me an example जहाँ पे you will figure out it upfront? And using backtracking search, you can solve n queens for n equal to 25. What does it mean you can solve? This means in reasonable time, right? So क्या क्वेश्चन पूछा था मैंने अभी? Right. So in this case, tell me, give me the best case जहां पे मेरे को constraints upfront शुरू में ही पता लग जाएगा. Let's say this is red. I assign this guy red. That's a violation, right? So I don't have to go all the way until the complete assignment level to figure out that there was a violation of constraints. So what will be next? What happens next in this case? Fine. But there was nothing special with this. You could have colored any of them. From here you come here, so we are just drawing part of a tree. Is this fine? This seems fine. अब प्रॉब्लम बताओ. नहीं, अब प्रॉब्लम बताओ. यहां पे अभी this tree looks fine, but अब मेरे को प्रॉब्लम बताओ. You have exhausted all the possibilities for South Australia, right? यहां से if you go and assign, sorry, not in this case. In this case, you still have blue as a possibility. In this case, all these three colors are neighbor of South Australia, so you know it here itself that this guy is going to create problems for me in the next level. Okay. So what should I do? backtrack, right? Now what will DFS do? How is DFS different from backtracking? Awesome. How is DFS different than backtracking? This looks like DFS, right? Yes. But how is this different from backtracking? So why are we calling it DFS plus backtracking? What will DFS do? DFS will not care all the way until complete assignment, and then you go and check whether it was violating the constraints or not, right? And keep on doing this. Always go to the last level and check whether constraints are violated or not. What will backtracking do? It will figure out somewhere in between that there are problems. So I don't need, so for example, I don't need to go this path. Even if I am not considering essay right now, let's say I color this red, I color this green. All these 5 guys are fine, but I know it here itself that essay is going to give me problems later. This will be an issue right now. I mean, there is no way for DFS plus backtracking to figure it out that essay will create a problem. ये अपन अपनी बात में बात कर रहे हैं. DFS plus backtracking does not have a way to figure this out. Okay? Right. So, what is this whole thing? एक बार कर लें इसको. Yes. And then 12 बजे आप लोगों की क्लास थोड़ी है. ओके 12 बजे बाद मीन्स या 12 बजे है?
12 बजे है सर.
आज अलग से रखी है, टाइम टेबल में नहीं दिखी मेरे को. है ओके. So then what I'll do is we'll take a 5-minute break and then we'll start from here at 11:15. Okay? इस क्लास की अटेंडेंस is over. So instead of making a video that is 100 minutes long,